Welcome to this OCP Virtual Global Summit presentation. BTDC, a practical demonstration of world-class efficiency. My name is Dr. John Summers. I'm the research lead at the ICE Data Center, which is part of Research Institutes of Sweden. Our head of lab is Torbjörn Minde. If you want to put a face to the name, there's a photograph here of me actively present in a panel discussion. This is a case study for the OCP community. The outline of this presentation is, first of all, we need to explain what the BTDC project is about briefly, and then we're going to talk about what we mean by holistic cooling control. Then we're going to talk about our testbed facility at RISE, which we have set up in order to redeploy the holistic cooling control first developed in the BTDC project. And then we're going to run a demonstration. This is a pre-recorded demonstration. If this presentation was live, we would have done a live demonstration. So this will demonstrate the holistic cooling control. And then in traditional fashion for a case study, there is a call to action at the end of this presentation. So what is BTDC? Boden Type Data Center is a EU Horizon 2020 funded project. It was funded under the Energy Efficiency 2017 initiative, bringing to market more energy efficient and integrated data centers. The proposed project that we put forward was to pilot a cost and energy efficient sub 1 megawatt prototype data center to be located in the north of Sweden. Our partners within this project are Eco Cooling, fresh air cooling company based in the UK. They have provided the project with the direct fresh air coolers. Boden Business Agency, based in Boden, of course, they have provided the project with access to land and power. H1 Systems, a Hungarian integrator that has built and commissioned the data center that I will show you in a minute. And then, of course, our partners at Fraunhofer in Germany, who have an interest in Industry 4.0 and IoT workloads, of which we have produced application-specific workloads to run on parts of the data center. This is funded by the European Commission, and the grant number is here if you want to find out more from the Cordis website. Where is Boden? It's in the north of Sweden here, relative to where Stockholm is in Sweden. You can see here on the map. So here's a picture of the data center that was built. This picture was taken in February 2019 when in the middle of the winter last year. And as you can see, this building here, inside there are 3 pods, data center pods. And one of the pods is configured to use OCP equipment. So it's configured in such a way that the central aisle within the 2 rows of racks is the cold aisle, and that is contained. So the cold aisle is contained. There are eco-cooling direct fresh air units towards the left here, which is on the left side of the building here. And this takes air from the outside, and then the hot air that is injected into the whole data center room here is either returned to the coolers and mixed with the outside air, or exhausted out of the building. So this is the configuration we have in Boden. Now, you can see inside the data center here, you can see we have legacy windmill servers here, 480 of them operating in 4 triplets. At the end here, you can see the picture of the eco-cooling units with the vents on the floor and the filters to provide direct fresh air. In this location in the north of Sweden, we have the cumulative hours between at below a certain temperature. So here you can see that below 20 degrees, we can operate for 350 days of the year. And the temperature can get below minus 30 here sometime during the winter. Now, the cooling units that we use have evaporative functions, so if we do get a very hot summer day, then we can wet the pads and evaporate water into the airstream humidify the airstream, but also to drop its temperature. So in these challenging environmental conditions of hot weather, we can use the evaporative function. And in the very cold conditions where we do not bring very much fresh air in, we recirculate a lot of the hot air in the data center, then we would need to humidify the air. So we've claimed world-class efficiency. So here we are using some open source software where we've collected the data from operating the data center for a year. And what we're showing here, the software that we use for the long-term storage is called Kairos DB. This is the web interface, and here I was able to interrogate the power usage effectiveness of the OCP pod. And this is starting back in February or March last year, where we started to run some experiments. You can see that the PUE fluctuates between 1.02 and 1.08 at the beginning here. There is no centralized UPS, which is why the PUE can go down as low as 1.02. And then we introduced this concept of holistic cooling control around about August last year. This is where we generated the ability to communicate information from the IT system to the ventilators, the coolers, and this enabled us to, by process control, to drop the PUE a little bit and get that under control. And then we did another experiment where we actually took control of the windmill server fans by putting a piece of hardware in. And that was actually presented at the OCP Regional Summit in September in Amsterdam. And from that point onwards, you can see that the PUE has been pretty much under control, irrespective of the workload that we've been operating from September onwards. And we've been below 1.02 most of the time. Bearing in mind that actually we are running through the winter here, so we do have a slight advantage there of not too hot weather outside. So redeploying this holistic cooling control, what we have done here with the support of eco-cooling, we have built one of our modules in RISE, which is in Luleå, the Research Institute, the ICE data center. We have kitted it out with 360 OCP Winterfell servers. So this is a later generation of OCP server. We've used the same cooling units as in Boden. So we got two direct fresh air cooling units. This is a room within a room. So we are taking the outside air is actually from the larger facility, which is being ingested through the coolers into the data center here. In contrast to Boden, we have a contained hot aisle rather than a contained cold aisle, so a slightly different configuration. And then so the whole data center becomes the cold aisle, and therefore we had to build some duct work in the ceiling for the two extract fans to be able to mix the hot air back with the coolers, or to actually reject the hot air out of the pod. Now, obviously, we don't want to reject the hot air into the outside room, so we're ducting this away, and this gives us the ability to measure the amount of heat that is available for any kind of heat reuse calculations that we are doing as part of some other experiments. The two boxes that you see in front of the coolers here, which are attached to the cooling units here, are climate boxes, which allow us to dial in the climate, which is part of another set of experiments. So we're going to run a demonstration of world-class efficiency. It's going to be a 10-minute brutal test regime on this module, where the maximum power that the IT load draws is 140 kilowatts. We're going to do a rapid change of load, a ramping up of load from 0 to 100%, and then ramping back down. And then we do a square wave where we go from 0 to maximum power, 140 kilowatts, and then back down again to see how the cooling system responds to this workload. We are monitoring the server microprocessor temperatures, and we're providing the server fan speeds and the microprocessor temperatures through Modbus to the cooling control system. And the cooling control responds to the server fan speeds, which enables us to do this holistic cooling control. Through the demonstration, we will show the instantaneous partial PUE. We will also do live calculations on the server-side Java operations per second per watt. This is based on the spec power of the individual servers, and then obviously aggregated across all servers based on their workload at the time. We're going to run the demonstration now. Here you can see this is the interface to the cooling control system that was produced by EcoCooling based on open source software. What you see here is a histogram of the fans, the server fans speeds. So this is information provided to this control system over Modbus. We're providing the microprocessor temperatures, so we can produce a map, a heat map like this, so we can see what the lowest temperature is and the hottest temperature is. At the moment, the servers are idle, they're doing no workload. Well, just at that point it was, and now we've started to increase the workload. So the blue line here is the IT power draw, and now you can see it's going from the 28 kilowatts, which it was at just a moment ago, and it's now starting to increase to 58 kilowatts. On the left here, we are calculating the partial PUE, the instantaneous value, which is also graphed at the top here. We are monitoring the chip temperature, the average chip temperature, and the minimum and maximum, which you can see produces the heat map here. So the temperature map you see here is based on the range of temperatures from the coolest to the hottest CPU. This is the arrangement of the racks. Rack 1 and Rack 12 are closest to the EcoCooling units, and we're monitoring the aisle temperatures of the hot and the cold aisle and the fan speeds of the EcoCooling units. So as you can see here, the pressure in the cold aisle relative to outside the room is 4 pascals, and the same for the hot aisle. So we've got no overpressurization of the hot aisle or the cold aisle relative to each other. The room is slightly pressurized, and you can see that we're measuring as the IT workload increases. You can see that we're measuring the server-side Java operations per second per watt as this ramps up to now 94 kilowatts to 102 kilowatts, and in a few moments we will be at 100% CPU load, which is around about 114 kilowatts, 120, 114 kilowatts. The EcoCooling fans are using 500 watts at the moment, so we have two extract fans which are operating at 20% and 2 supply fans which are operating at 35%. The supply fans are operating at 35% based on the fact that the average server fan speed is at 20%. As the IT power increases, you can see that the chip temperature increases here. Now we're at the hottest temperature is 74, but the average temperature is 60 centigrade. And the calculated workload or the calculated IT efficiency has gone up from 0 to around about 5,000 server-side Java operations per second per watt of power consumed by the whole module. So we're monitoring the power of both the IT and the facility when we do that calculation. Pressure remains stable, fan speeds of the server remain stable, and the fan speeds in the coolers remain stable. So nothing has changed just yet. Everything is under good control as we let the temperature of the CPUs rise. This solid red line here shows the CPU temperatures, red on the right axis here, and this is now reaching its average maximum of around 70 degrees, 67 degrees here. The histogram of server fan speeds is moving to the right. Now it's going to start moving to the left because now we're dropping off the workload. You can see it's dropping down to 85 kilowatts, and then that's now going to drop down to the idle power in a few moments. So I'm going to speed this up a little bit just to get it back down to idle. as the experiment runs. The fan speeds are all the same, 20% server fan speed, 35% on the cooler fan speeds. And as we go down to 0, so now we're down to 28 kilowatts, which is the idle power, and the histogram of server fan speeds has moved to the left. Chip temperatures have dropped down now to lowest at 37 and the hottest at 56. The average is 47. Still only using around about 500 watts of power to run the extract fans and the supply fans. And the PUE you can see there, so the hot aisle temperature is now at 36 degrees centigrade. Cold aisle still maintaining 21 centigrade. So we remain at idle for about a minute, and then this workload was generated using stress-ng. Stress-ng can stress the CPU, so you can invoke a number of cores from the CPU. Now we're going to run using M prime. So M prime will stress all of the CPU and all of the memory. So instantaneously, when we switch this on, the workload on all 360 servers simultaneously, we jump up to 150 kilowatts. Straight away, the CPU temperatures start to increase rapidly, 55, 60 centigrade average, hottest at 77. And now we are stabilizing at around about 140 kilowatts. There's a bit of a jump peak there. Server fan speeds haven't really changed much. The histogram has slightly moved to the right, but the average is still rounded to 20%. The eco-cooling fan speed is 35%. The extract fan is still at 20%. But you might be able to see the histogram slightly moving towards the right now as this persistent heavy workload sits on the data center. And we're using peak 140 kilowatts. At some point, the average of the server fan speeds will increase and then the eco-cooling fan speed will respond to that immediately because of the communication that we've developed over Modbus between what the servers need in terms of their airflow and what the supply fans can give in the eco-coolers. Right, we've just gone to 21% now, and so the eco-cooling fans has gone to 28%. The extract fans are synchronized to the supply fans, and so they have jumped a little bit. So with a little bit of a speed up, because now it's getting the microprocessor temperatures are a little bit hot, so the servers are saying now I need a bit more air to cool these down. Now 22% is the average server fan speed here, you can see, and the histogram is moving towards the right rapidly. The workload has jumped off the data center now. You can see that we've just rapidly jumped back down to idle power, slightly more than 28 kilowatts normal as the fans start to slow down. Everything has slowed down back to normality. The chip temperatures has dropped down to 56 centigrade immediately. So you see there was a little bit of a jump in the supply fan speeds. So what do we mean by holistic cooling control? I mean, we said it was a communication issue, really, just a process control communication issue. So what this demonstrates here, this graph demonstrates here, here's the workload. So we ran this workload, this is the timestamp where we ran it, the same workload that you've just seen in the demonstration, but this was run under standard cooling control. So what actually happens here, the standard cooling control, the normal way of doing this is to have a set point temperature, and then what happens is as the workload comes onto the data center, it starts to challenge the cold aisle temperature, and so it starts to challenge the hot aisle temperature, I guess, and then there's a lag. This is the important thing, is a big lag because the coolers are responding to the increased temperature, which has come and gone in a sense, all the workload's come and gone, but the temperature has been read just at that point. So you can see the supply and return temperatures here for the cooling, the eco coolers, and you can see the rack inlet and outlet temperatures here. We turned the coolers into holistic cooling mode, and what you can see here is that we didn't really need to do this big jump here. By a little bit of clever control, process control, we only needed to ramp up the fans just slightly at the point when the maximum load was running for just over a minute. So you can see here the contrast in the two, that the energy saved in fan energy saved is substantial. In terms of the temperature seen by the IT, pretty much the same. In terms of the set points, in terms of the supply and return temperature within the hot and cold aisle, that's the same as well. So in summary, this demonstration has highlighted the importance of holistic cooling control. By simple process control, we can achieve this simply, but we need to synchronize the cooling of the coolers to the demands of the IT. And we've done this by adopting a number of open source software tools and standards within a process control loop. So this indicates that there's potential improvements in data center energy consumption by this improved communication. So our call to action then to the community, we believe that the best place to create the communication from the IT equipment to the cooling equipment is at the rack level. So we could appeal to the rack and power sub project within the OCP to consider maybe making the open rack intelligent. So this is providing a little bit of hardware that can enable any cooling system which uses a number of different protocols from the HVAC community, provide this information such as delta T, microprocessor temperature, average microprocessor temperature, airflow through the rack, and maybe the thermal power consumed by the rack. So we have intelligent PDUs, power distribution units for power, so we can monitor the power of a socket. Why couldn't we have an intelligent rack for cooling? So this is our call to action, and we would like the rack and power community to maybe consider this as an option, as demonstrated by our presentation here. I would like to thank my colleagues at RISE who helped to make this demonstration run at RISE. So that's Eric, Miko, and Jeffrey here, and also our collaborators from EcoCooling, Alan and Toby. If you want to find out more about the Bowden Type Data Center, please go to the website here, bowdentypedc.eu, where you will find a bit more information. And if you do require information that you can't find there, or you have any questions about what we've done, please do contact myself, John Summers, with my email address and Swedish telephone number there. Or you can, if you can't get hold of me, you can contact our head of lab, Torbjörn Minde, on that email address there. And I'd like to thank the financial support from EcoCooling to undertake the demonstration within RISE, and also the funding from the EU for the Bowden Type Data Center. I hope to receive some questions. I look forward to that, and I thank you for your time. Thank you very much. Bye-bye.